Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, now we take a look at example of refrigeration system. So you have a refrigerator that use R134A, which is the refrigerant, as the working fluid and operates on actual vapor compression refrigeration cycle between 0.4 megapascal and -10 degree at a rate of 0.05 kg per second and lives at 0.8 megapascal and 50 degree. The refrigerant is cooled in the condenser to 26 degree and 0.72 megapascal and is throttled to 0.15 megapascal. Okay. So you need to determine the rate of heat removal and the power input, the isentropic efficiency of the compressor, and the COP of refrigerator and heat pump. Okay. So basically you have your problem is actually actual vapor compression refrigeration cycle. Okay, so how to differentiate between ideal and actual? Whether is directly given to you, something like this, actual, or perhaps you have something like this, okay, isentropic efficiency. So meaning your problem is actually an actual cycle. Or perhaps if there is no isentropic efficiency mentioned in the problem, but there is a process of subcooling or temperature rise before compressor. Those also can become what we call as an actual cycle instead of ideal cycle. So let's get back to our problem. So first what we need to do is we need to draw the TS diagram. So let's draw the TS diagram. Okay, what you need to have basically in your TS diagram is the saturation line and then two pressures, okay, before and after compressor. Okay, next take a look at your problem. Okay, basically here, even though you have four pressures, 0.14, 0.8, 0.72 and 0.15, but the thing is 0.14 and 0.15 is actually almost the same. 0.72 and 0.8 also another pressure. So yeah, basically you have two different of pressure. Okay, why this value have 4? Because of 0.14 and 0.15. Then this is what we call as the temperature rise before compressor. 0.8 and 0.72, this one is because of subcooling. Okay, later I will explain further regarding this one. Okay, so next take a look at the first statement. The first information given. So you have 0.14 megapascal and -10 degree. So this one should be state number 1. because this one occurs at lower pressure. So you have P1 equals to 0.14 Okay, now what we want here is actually H1 and S1. The value of entropy at state number 1 and the value of enthalpy at state number 1. Okay, next we need to check whether this state number 1 is actually falls on top of the saturation line. So how to check this is you need to refer to the property table. So we're going to use this pressure and this temperature as guideline. Okay, our refrigerant is R1348. So this is table, property table R1348. So take a look at pressure 0.14 megapascal. So meaning this one, right? 140 kPa. So suppose at 140 kPa, the saturation temperature is actually negative 18.77. But your problem is actually negative 10 degrees C. Okay. So meaning at saturation line, this one should be negative 18.77. But here is actually negative 10. So negative 10 is so basically you have what we call as a temperature rise. So this is state number 1. So not position on top of the saturation line. Okay, that's the first judgment. Now we know that state number 1 does not fall on the saturation line. Next, we want to have these values, okay, enthalpy and entropy. So we go back to the property table. So we are not going to use this, okay, since we know our problem is actually superheated. This one is superheated region. So we're going to go to superheated table, which is table A13. Okay, in fact, if you want to refer the value of temperature on the saturation line, also you can use the superheated table. As you can see here, P at 0.14 megapascal. The saturation line temperature is negative 18.77 degrees C. The same, right? Okay. Now we want the value of H. So our problem is actually negative 10 degree. So meaning our H1 is 246.36 and our S1 is 0.9724. Okay, done. So that's all the info that we need from state number 1. Okay, next we go to the state number 2, right? Okay, let's put it something like this. Since you know that your problem is actually actual vapor compression cycle, and you have another additional information, supportive information, which is you're gonna calculate later isentropic efficiency. So meaning at the compressor, right? So meaning at this position, you're gonna have something like this. Just directly draw this one. So I want to make this one longer. Okay. So this becomes state number 2S. Okay. This one is actually state number 2A. Okay, this is the actual. Okay, this one is actually the what we call as a isentropic process. This one is the actual. So the one that lifts up from the compressor is 0.8 megapascal and 50 degree, meaning this one is actually actual. So state 2A, 0.8 megapascal, and then your D temperature is 50 degrees. Okay, some put it P2A or T2A to represent the same, which is the one that we put it here, 2A. But I myself just put it as P2 and T2. Okay, meaning actual also, right? So this will become 0.8 megapascal. Okay, now we want to find H2. Okay. So H2 is at 0.8 megapascal. This one, and temperature is 50 degree, 286.69. So H2 is 286.69. Done. Okay, the one is for state number 2. Okay, later we're going to discuss what is state 2S. Okay, so we just go directly to state number 3. Okay, then the refrigerant is cooled in the condenser. Okay, cooled in the condenser to 26 degree and 0.72 megapascal. Okay, so it cools down in the condenser. So this region is actually condenser until 26 degree and 0.72 megapascal. So state number 3. is actually somewhere here. So the same like this one. So we're going to analyze the saturation line. So where does the state number 3 falls? Either on top of the saturation line or not. Okay, so how to judge that is basically once again look at the property table. Now we're going to refer at 0.8 megapascal. Okay. So we are not going to use the superheated because now our problem is actually at the saturation. Okay, 0.8 megapascal is 800 kPa, which is this one, right? So it occurs at temperature should be 31.31 degrees C. But our problem is actually at 26 degree. So basically, the state number 3 does not falls on top of the saturation line, but just lower than the 31.31 degrees C, which is 26 degree C, and at pressure of 0.72 megapascal. So that's how we judge state number 3. So this becomes state number 3. So in order for us to find the value of H3, so we have P3 so we are going to refer instead of pressure table, we're going to refer temperature table at 26 degrees C, right? 26 degrees C. So at 26 degrees C, which is this one. Okay, now you have option HF or HG, which is enthalpy at liquid or enthalpy at vapor state. So obviously this one is liquid, right? Okay, I remember I explained at this region is actually liquid. So at 26 degrees C, it's gonna be saturation liquid. So this value 87.83. So H3 is 87.83. Okay, next we go to state number 4. State number 4 is what we call as a throttling process. The enthalpy will be the same. Okay, so H4 also 87.83. Okay, done. So now we have all the information that we need. Okay, in order for us to find the answer. This one is state number 4. State number 4 always occurs in the mixture region. Okay, mixture region, or we can call it as a low quality because of mixture. Low quality meaning you have two phase there, liquid plus bread. Okay, now let's answer the first question. The rate of heat removal from the refrigerated space. Okay, refrigerated space meaning the one that we want to cool down, meaning our box in our refrigerator, right? So the amount of heat removal, so it's actually here. Okay, so this one is actually Q dot L. So number 1, Q dot L is equals to M dot H1 minus H4. So you put in all the values, so what you get is 7.93 kilowatt. So the rate of heat removal from the refrigerated space. Okay, we put a box here. Here you're gonna have what we call as a cooling coil. The box at initial state is actually room temperature, and due to difference of temperatures, the heat from the box will go towards the cooling coil. Okay, so it's actually a refrigerated space. Next is power input to the compressor. Okay, power input to the compressor is this one. Okay, so we're gonna use 2A. So work compressor equals to M dot H2 minus H1, or we can put it as H2A minus H1. For me, 2A and 2 is the same. Okay, so the answer will be 2.02 kilowatt. So done for number 1. Next we go to number 2. Okay, number 2 we talk about isentropic efficiency. So as I mentioned previously, efficiency of compressor, which is isentropic efficiency, is pendek bahagi yang panjang. Okay, efficiency, right? So meaning H2S minus H1 divided by H2A minus H1. So that's how we want to find our isentropic efficiency. Okay, so basically we have H1 and H2A, but we not yet have H2S. So in order for us to find H2S, we need to find the state number 2. Okay, at state number 2. Sorry, at state number 2S. So at state 2S, P2S is still 0.8 megapascal. Okay, so the other information that we have is, take a look here. So this is S, right? TS diagram. So this one is actually straight line. So we're gonna use this one. S1 is actually equals to S to S. So S to S equals to S1, which is occurs at, which is the value is 0.9724. Okay. So in order for us to find H2S, we need to refer the superheated pressure at 0.8 megapascal. Okay. So we're going to go to the property table and use this entropy value. Superheated. Okay, superheated. So 0.9724 is actually in between this one, right? 0.9724. The one that we want is actually H value. This one this one X in between 276.45 and 286.69. So what you need to do is you need to do interpolation. Okay, so I believe you know how to do interpolation. So from there, the value of H2S is 284.21 kilojoule per kilogram. Okay, so put all the corresponding value into this equation. So you're gonna get the isentropic efficiency for the compressor is 0.939. So it equals almost 94%. Okay, next we go to question number 3, which is finding the COP. First, COP refrigerator. Okay, so COPR is actually equals to Q dot L divided by work dot in, which is work dot compressor. So from there, you're gonna get 3.93. Okay. Next is COP heat pump. COPHP is actually Q dot H divided by work dot in. Okay, so Q dot H is actually this one, the heat transfer to the surrounding. So how to calculate this one is m dot H2A minus H3 divided by work dot in. So from there what you get is I don't know the value, so we just need to calculate this one. Alright, so m dot multiplied by H2A minus H3 divided by work dot in. Okay, so I think that's all. Basically you've done with the almost done with chapter 5. So this is the actual cycle. So I also already explained how actually ideal cycle. Okay, even though we do actual cycle. So for ideal cycle is the one that value that directly position on top of the saturation line. So that's all. So the calculation will be the same. Okay, I think that's all. Assalamualaikum warahmatullahi wabarakatuh.